Okay, a few other examples of uses of series. We can use them for limits. I understand you could evaluate this limit using L'Hopital. Let's take a look at how you do it with limits. So we want the limit as x approaches 0. Instead of e to the x, we are going to use the Maclaurin series. And that has terms 1 plus x squared over 2 plus x cubed over 3 factorial, and so on, minus 1 minus x all over x squared. The 1 and minus 1 cancel. The x and the minus x cancel. Now we can take the remaining terms and divide each of them or factor out an x squared and cancel it. This idea of factoring out like terms and canceling them will become useful or will prove useful on your homework as well. If I divide everything by x squared, I get 1 over 2 factorial plus x over 3 factorial plus x squared over 4 factorial plus x cubed over 5 factorial. And if I let x equal 0, everything is 0 except the first term, which is 1 over 2 factorial, or 1/2. Another use for a Maclaurin series is with multiplying functions. So we only want the first 3 non-zero terms, mainly because after about 3 or 4 terms, it gets pretty messy. So we're going to take e to the x times sine x. E to the x, again, 1 plus x over 1 factorial plus x squared over 2 factorial times sine x. X minus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. So to multiply, I'm going to do exactly what I would with any other polynomials. Use something similar to FOIL. I'm going to take 1 times each term. And again, it would help if I wrote these correctly. This should be x to the 5th over 5 factorial. And then take x over 1, and I Again, I'm going to rewrite this to give myself a little bit of room. X over 1 factorial times x would be x squared over 1 factorial minus x to the 4th over 3 factorial. And I'm going to stop there because the next term would be x to the 6th and would be too much. The last bit of multiplying I'm going to do, x squared over 2 factorial times x is x cubed over 2 factorial. And then I would have minus x to the 5th over 2 factorial times 3 factorial. And now I'm going to add. And I can stop with my third non-zero term. So the x I get x squared over 1 factorial. And then I have minus x cubed over 3 factorial plus x cubed over 2 factorial. This is x to the 3rd over 6 and x to the 3rd over 2. For part B, we want to evaluate tangent of x. Well, tangent of x is sine of x divided by cosine of x. So if I look at, again, the series that makes up sine of x and cosine of x, and because it's a fraction, I'm going to divide. So I'm going to just write 3 terms. And I'm not going to write the factorials. I'm actually going to multiply them out. So using long division, I look at what do I need to multiply 1 by to get x, and the answer is x. Multiply each of the terms outside by x. And then I'm going to subtract, which is the same as adding the opposite. Finding common denominators, that's going to be 3x cubed over 6. When I combine those, I end up with 2x cubed over 6, or 1/3 x cubed. And minus 4x to the 5th over 30, and I bring down the x to the 7th. I need to multiply 1 by 1/3 x cubed. And subtract. In my first terms, 0 out. If I find a common denominator of 30, get x to the 5th over 30. Minus 71, 72, 71 over 5040, x to the 7th, and there'd be other terms here. I really only need that first term. I would multiply x then by x to the 5th over 30. So tangent of x, the first 3 terms, would be x plus 1/3 x cubed plus 1/30 x to the 5th.